Okay, yeah, let's resume the class. So next we are going to introduce a concept called coset. But the purpose of this coset is to help us to prove Lagrange theorem. So what is Lagrange theorem about? Lagrange theorem relates the size of a subgroup to the size of a group. Let's do some example and see if you figure out some interesting property about the sizes of a subgroup and the original group. So for instance, let's say this is a group that has this is the degree of rotation, and this star represents successive rotation. So if I have 2 degrees star 7 degrees, that means that I have a total 9 degrees of rotation. Is that okay? Now, the size of this group, or we call it the order of this group, this one has order equal to what? The order is equal to 360 because there are 360 elements there, right? Now, we have seen some example before. If we do not take all these elements, let's say we just take 0 degree, 120 degrees, 240 degrees, and then star. This is a subgroup, right? And then the order of this one is equal to what? Order of this one is equal to 3. Is that okay? Now, can we come up with other examples? So, are there other examples of subgroup of this one? Are there any other example? Well, maybe this one. 0, 60. Is that okay? 120, 180, 240, 300. Together with this star operator. This is also a subgroup. Why is it a subgroup? Because we just need to check whether it is closed. It is easy to check that it is a closed operator. Right? Applying any two things, 120 and then 300, you get 420, and then which is equal to 60. And 60 is there in the set. So it is a closed one. And then for this one, the order is how many items are there? 1, 2, 3, 4, 5, 6. Is that okay? Right? So what's special about the order? If you look at this, so you can have order of 4. Like you take 0, 90, 180, 270, right? You can have order of 180. You get 2, 4, 6, blah, 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 up to 358. And then together with 0, okay? So it seems that we have this observation. So the order of a subgroup always divides the order of the original group. Okay. So this is Lagrange theorem. Lagrange says if the original group has finite size, any subgroup of this original group, the order of the subgroup must divide the order of the original group. Okay, so this is Lagrange theorem. And then to prove this, we just need to make use of a slightly, a little helper. So this is a concept called coset, which helps us to show Lagrange theorem is correct. So what is the coset? Let's see. So here, let's go back to more basic things. So we are not talking about group here when we define cosets. So let's look at an algebraic system which has a set A and an operator. Just a set and an operator. This operator is binary, and it is not necessarily a closed operator. So very, very basic algebraic system. You just have a set and an operator. You don't care whether it is closed or not. Okay. And then suppose that we have some subset of this A and some elements of this A. Then we can define two sets Okay, one has the notation of A star big H. A star big H is the set that contains all the elements of this form A star little h. Is that okay? So you get all the elements of H, you multiply A on the left hand side, and then you get the resulting items. You collect them together. It is called A star big H. Is that okay? So similarly, you can take a look of this notation. It is easy to see. You know what is A star small h. It is just something, right? A star big H, because H contains many things, maybe H1, H2, H3, a lot of items. So A star big H is the collection that contains all the A star H, all the possible cases of A star H. Is that okay? And similarly, this is big H star A. It is a set that contains all the items of the form H star A, where H is in big H. Is that okay? Is that okay? So one is to apply A on the left-hand side of H. We call it a left coset. And then one is to apply A on the right-hand side of H, and we call it a right coset. Is that okay? So this is the concept of coset. Very, 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 very easily understood. Okay. So for instance, let's look at this one. So this is an example. So this one is an algebraic system, right? And then this is a subset of this one. Is that okay? So we can have this one is equal to H. Is that okay? Now we can talk about some item A. Okay, so let's say A is the item 40 degrees, which is inside here. Okay, then we can get what is A star H. A star H will be equal to 40 degrees, 120 degrees, and 160 degrees, and 280 degrees. Is that okay? That's it. And then it turns out that, okay, because this is a commutative operator as well, so this is going to be equal to H star A. Is that okay? Okay, for this example. Okay, that's it. This is the definition of coset. Good. So you can have a different H. So let's say you have a different H prime. Okay, let's say this H prime. Let's say you can have something like 100 degrees, 170 degrees, something like this. And then you have another A. Let's say you use 40 as well. Then this time you can have A star H to be equal to 140 degrees and then 170 degrees. Okay? Is that okay? So this is the definition of coset. Now, but we are talking about groups. So let's get back to what happens when we have groups. Okay. So this is the theorem. So theorem. Okay, now suppose that the original algebraic system A star is a group. Is a group, and the H is not chosen randomly. The H is also H star also is a group, so H is a subgroup of A star. Okay, then if we look at two different cosets, let A star H and B star H be the cosets. be two cosets of H. So one is multiplying A on the left-hand side, and the other is multiplying B on the left-hand side. Then, either these two things are the same. So either A star H is the same as B star H, or they are disjoint. Okay. Okay. So we have actually an example here. So for instance, we have a coset A star H when A is equal to 40, 160, 280, right? And then it happens that if you look at this H, H star is also a subgroup. Okay. Now let's take a look of another B. Okay, let's try B is equal to 50. So when B is equal to 50 degree, what will happen? Then we will have B star H is equal to 50 degree, 170 degree, and 290 degree. Is that okay? And then let's try another one. Let's try C. Okay, let's try C. C, let's try 280 degrees. Is that okay? Then what will happen for C star H? C star H is you get 280 degrees, and then 280 plus 120 is 400, right? 400 degrees is like 40. Okay, it's 40 degrees. And then you have 280 plus 240 is 520, right? So 520 is like 160. Good. So you look at this, A and B, they are disjoint, nothing in common. But A and C, they are not disjoint, and actually they are exactly the same. So we want to show that, okay, this H is something very special, okay. So H can be used, okay, if H is a subgroup, then the cosets of H will either be identical or they are completely disjoint. So they won't be just overlapping apart and then have some other items that is not common. Is that okay? So either identical or completely disjoint. Okay? So what is the effect of having a theorem like this? If this is true, then what will happen? Then the items of the original set A, like this one, is going to be partitioned, okay, into different cosets. So 40, 160, 280 in one coset, 50, 170, 290 in another coset, right? And then what? And then 121, 241 in another coset. Is that okay? So we can have a lot of cosets, and then that partitions the items of the original set. And then if we can further show that the size of each coset must be the same, then in that case what? The order of the coset, the order of the subgroup must be dividing the order of the original group. Is that okay? Is that okay? Because we can use this subgroup to make the original items here forming cosets. One coset, two cosets, three cosets. Each coset has the size of the subgroup. And then it covers all the elements of the original group. So it means that the order of the subgroup divides the order of the original group. So this is Lagrange. Okay? So this is a key theorem. Okay? So we need to prove actually two things to get Lagrange. One is the coset has this property. It has a partitioning property. The other one is every coset have the same size. Okay, these are the two things. This is more difficult. The other one is easy. Okay, so let's get the proof for this one. Proof. Okay, what do we need to prove? So we want to show that they are either disjoint or they are the same. So let's assume that they are not disjoint. In that case, we want to show that they are the same. Is that okay? Okay, so proof. Assume that, so we just need to check, assume that they are not disjoint. A star H and B star H are not disjoint. So not disjoint doesn't mean that they are the same, right? But not disjoint means what? So if two sets are not disjoint, what does that mean? They have a common element. Is that okay? So we let F to be a common element. Let F be a common. They may have many common elements, but let's say F is one of them. Common element of these two cosets. Okay, F is a common element of these two cosets. What does it mean? So F is an element of the coset A. So F is equal to A star H1 for some H1. Is that okay? And then F is an element of the coset B, B star H. So F is equal to B star H2 for some H1 and H2. Is that okay? Is that okay? Okay, so now we have A times H star H1 is equal to B star H2. Now remember, H are elements from the big H. So it has inverse. So there is some inverse of H1 defined in the big H. Is that okay? So we can write down A is equal to B star H2 star H1 inverse. Is that okay? Is that okay? Does that make sense to you? Because we have A star H1 is equal to B star H2. Now because H1 is from the group H. So the inverse of H1 exists. So we take out the inverse. Let's call it H1 inverse. Okay? Multiply to both sides of this equation. Then the left hand side will become A star H1 inverse. So it's A. And the right hand side, B star H2 star H1 inverse. That's it. Okay? Now, so here we have A can be, so what is A? So now A can be expressed as B star, something like this, right? And then H2 is in H. H1 inverse is in H. So the product is also in H, right? So actually we have A is in the coset. A is an element in the coset of B star H. Right? Because there is B multiplying some elements of H. So you can think of this as some H3. So A can multiply some H3. A can be expressed as B multiplied with some H3. So A itself is in the coset B. Okay? But we not want to show more. We want to show everything. We want to show everything in the coset of A star H also is in the coset of B star H. We want to show more. Okay? Well, let's try. Okay? So everything in the coset of A star H, so let's call it A star H. Okay? A star H would then be equal to B star H2 star H1 inverse star H. Is that okay? And then this is a whole thing. So this is equal to B star some H to the H3 or H4, whatever. And then this is in B star H. Okay. So after doing a lot of things, we have shown what? We have shown that A star H is a subset of B star H. Anything that you can imagine appearing in A star H, it is also in B star H. You can repeat these arguments so that you can show B star H must be a subset of A star H, so that the two sets are identical. Is that okay? So although this is very complicated, this is like H star something star H, right? But then, if you still recall, everything here is in big H. H is a group. So the multiplication of all the things together is closed. So it is also equal to a certain element in the big H. So if it's in a certain element of big H, let's call it H3. So B star blah 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 is equal to B star H3. And by definition, if A star H can be expressed as B star H3, then A star H will be in the set of B star big H. Is that okay? That's it. Okay? That's it. So we have shown this thing, okay. Using a subgroup, you can partition the items of the original set A into disjoint cosets of that group H. Okay? And then next, okay. And then next,